Hi, this is Coach Ed, and I'm going to provide a little bit of scaffolding for some of the homework problems as they become a little more tricky in this section. So, turning to page 57 in your book, problem B71, this one talks about the U.S. Census Bureau taking a census every 10 years and the population growing over time. So, just changing the numbers. Suppose we said that in 1990, the population was 248.7 million, and in that there was a model that expected the population to grow at 1.5% per year. Well, that would be an equation something like this. F of x equals this initial value, right? Initial value in 1990 would be 248.7 times a multiplier. It's growing at 1.5%. Remember, when you're growing at 1.5%, you have to add that to 1. So the multiplier becomes 1.015, and then it's per year, so I'll use to the x. That's how many times we're going to compound it. So that would be equation for how many years after 1990 the population was. So if somebody asked me in 5 years, let's say 1995, what would the model have predicted? I would say, okay, f of 5, that's 5 years from 1990, equals 248.7 times 1.015 to the fifth. And if I plug that into my calculator, I will get a result. And I'll let you do that. It also asks something about what is the residual if you knew that in 10 years a population was something else. So I do know that the population in 2000 was 281.4 million. Okay, so 281.4 million in 2000. In 1990 it was 248.7. So what happened there? So what happened was that f of 10 in 10 years, okay, we had equals 248.7 times 1.015 to the 10th, right? I'm going to plug that into my calculator right now. I'm going to say 248.7 times 1.015 to the 10th equals, and I get a number 288.6. Okay, now what is the residual? Well, the residual is the difference between our model. This is our expected. If we expect it to grow 1.5%, we expect it in 10 years to be 288.6. It turns out that actually we only had 281.4. So the residual equals 288.6 minus 281.4 equals 7.2 million. In other words, our estimated model of 1.5% actually ended up higher than the actual number. So the growth rate in population was actually slightly less than 1.5%. Ask you to solve systems of equations that are not linear functions. We're used to having these things look like lines, and now suddenly we're looking at exponential functions. Now, how do we solve something like this? Well, elimination generally does not work for something like this if these terms have different powers. This one has a times b squared. This one has a times b to the fourth. So elimination is not going to work. However, substitution is a good candidate. So let's take a look at the first equation. 64 equals a times b squared. We could rewrite this to solve for a by dividing both sides by b squared. So let's start with this equation. I'm going to start with 64 equals a times b squared. I'm going to divide both sides by b squared. And that's going to leave me with a equals 64 over b squared. Once I have this, I can substitute that a back into the second equation. So let's do that. 256 equals a, which we know also equals 64, divided by b squared, right? That's this a part right here, times b to the fourth. Whoa, now I'm left with something kind of interesting. These cancel out. Okay, b to the fourth divided by b squared is b squared. And we know that because b to the fourth over b squared equals b to the 4 minus 2 equals b squared, right? So 256 equals 64 times b squared. I divide both sides by 64, and now I'm going to have b squared equals 4. Well, if b squared equals 4, I know b equals 2. Anyways, that hopefully will help you with these B72. Okay, B73 is talking about one of these fancy exponent problems. And how do you rewrite this thing by breaking it apart? Well, one strategy that they talked about here is just separating everything. So we have this is 5 times x to the third times 1 over x to the minus 2 times y to the negative 4 divided times 1 over y to the fifth. Well, how do we get rid of all these negative exponents? Well, let's look at it. This is 5 times x to the third. The negative exponent on the bottom becomes a positive exponent if we bring it to the top. So this becomes x squared positive. If we want to change this one here, to a positive, what do we have to do? We have to bring it to the bottom, y to the fourth. And then this one stays the same because it's also already a positive exponent. So here we go. So what do we have? We have 5 times x to the third and x squared at the top. So we have x to the fifth. And on the bottom, we have a y to the fourth and a y to the fifth, which is y to the ninth. Whoa. What happened there? Okay, which is y to the ninth. So hopefully this will give you some ideas on how to solve the one B-73. Okay, finally, last two questions I'm going to help you with is, let's talk a little bit about t to the n equals some function like a times b to the n versus f of x is a times b to the x. The difference between this is that t to the n represents discrete functions, which means the n, this thing, can only be whole numbers. So you'd have a graph that looks something like this. Here, 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 here. Okay. Whereas because there is no such, you can't have an n that's 1.5. This is 0. This is 1. This is 2. This actually could go negative as well. But in a continuous function, f of x equals a times b to the x, the difference is x could represent a half or a quarter or a square root of something. In other words, it could be any number along this line. So it's a continuous function. Okay. And finally, 76. we have, imagine, I got a different example of a 5,000 gallon tanker, gas tanker, that goes around filling up gas stations. So what would the graph of the tanker volume look like at every successive stop, right? So he has made 0 stops and he's got 5,000 gallons, right? What happens after he makes 1 stop at a gas station? Well, let's see. He's at 500, right, the whole time. Oop, at 1 gas station, oop, is at 4,000. Oop, at 2 it's 3,000, 2,000, 1,000. Oop, to 0. 3, 4, 5. Now we're at 0. Okay, hope that helps.